Hello, I'm Francesco Paci, and I'm working as an application engineer at GreenWaves Technologies. We are a French-based company uh, which we design a family of chips which enable artificial intelligence and machine learning at the edge. Let me present a little bit this new paradigm that we see that everyone's moving. So we are passing from a data streaming paradigm, which we sense data and then we send the data through a network medium, and usually we have a cloud or centralized data processing. And what we've seen in recent years is that all the analysis of the data and the processing is moving to the sensor, so closer to the data source, and then data is sent through the network already processed. This new paradigm has a lot of benefits. So it can avoid cloud congestions. It can help privacy because sensible data, can just stay in nodes and be processed there without without sending it through the network. And also the decision latency, because the data and the decision can be taken close to where the information is. But we have an energy issue. So usually we have less availability of energy in sensor devices. So how we cope with this and how we try to solve this new paradigm? We design a Gap8, an IoT application processor, which has three main characteristics. So the first one is that we have high computational power at low power. So we stays under the 100 milliwatt, while we can go down to few microwatt when the processor is sleeping. It's very agile, so can move between state. We will see. I will present them: sleep and sensing, or data processing in a few cycles. And it's also flexible, so it's not an accelerator or few algorithm, but it's a fully programmable processor, general purpose processor. So here is the architecture. So we can see on the left, it's what we call the fabric controller, which is you can see there are the blocks which are of a classical MCU. So there is this fabric controller block, which is a RISC-V core. Then we have all on the left all the peripherals to communicate with with the external world. And also there are 512 kilobyte of main memory, and the debug and power management unit. And then on the right, we have what we call a cluster, which is a cluster of 8 cores, plus an hardware convolutional engine that can speed up convolutions. We can do three by three convolutions in one cycle, or one 5 by 5. There is the core shares all the cores share an L1 memory of 64 kilobyte. So how do we scale proportionally to the demand? So we can, while duty cycling, for example, waiting for data or to be awakened by a PIR, or awake from time to time to sense, we can consume a few microwatt, and the L2 memory can be retentive to keep data there. And then we can sense data, turning on the fabric controller and consuming around a few milliwatts. And then we can turn on the cluster, and depending on the frequency we are running, we can consume a few tens to few tens of milliwatts. Okay, so but the architecture is can't be fully exploited without tools, and different users are expecting different kind of tools. So some user expect just a package solution that is working. Some other needs automatic porting of neural network or other machine learning algorithm, or like filtering algorithm, classical computer vision algorithm, or other are expecting something which is revolutionizing the world. So each of these different users expect or a solution or something which is prepackaged and is fine-tunable, or expert people just need a chip with the architecture and they write bare metal code. So in our software offer, we have what we call the GAP SDK, which contains a RISC-V GCC compiler, a virtual platform that we call GVSOC, which is quite accurate. So the cores are modeled inside and have between 5 to 10% of error, while we try to keep for a full application the error 150%. And this is very useful for debugging and for profile code to find bottlenecks and find where we need to improve our code. Then we have some RTOS that we support. PulpOS, which is a historical pulp project, which is a university project of a family of chips and architectures based on RISC-V. We support FreeRTOS and Zephyr, which is a well-known RTOS, quite young, which is well adopted in the RISC-V community, and also a common API to write code and to exploit different RTOS without needs to rewrite all calls to driver to cluster. So, and then we have Gapflow, which is a suite of tools for neural network, but not only. So, if we want to, on the chip, we can directly write cluster code. So, but we need to manually parallelize it and move manually data from different memories. Then the first tool that will ease memory movement that we provide with our suite of tools is called AutoTiler, which is a graph description and also an automatic memory movement generator. So you can describe which is the flow of the data and the size of them, and then the tool will automatically generate code to move data back and forth in the different memories, and also if there is an external RAM which is out of the chip. Then we have what we call NN tool. It's a neural network tool which automatically converts TensorFlow-like models, which can be quantized or not, to an AutoTiler model, and then the code can be directly mapped on the chip. And in this NN tool, also we support two different post-training quantization. And then we have a model library, which we call NN menu, which is giving several examples of well-known neural network, like, for example, the MobileNet family, SqueezeNet, and the Visual Wake or Challenge Network, KWS. And in these model libraries, anyone can take one of the example and use in his own application. And also we provide few reference platform, which are boards with also the code for specific use cases. So the features of this full Gapflow, it's that these all the examples are made based on makefiles and are open source. There is an NN neural network focus, but not only. We have also other algorithms, like, for example, for filtering, like, for example, FFT. The idea that we use to build this tool is that anyone can use one of these tools or more than one, or just none. It's extendable because it's open source, and there are clear points of failure. And these are, I already said, and it comes with some examples that explain how to use all the tools. So let me present a couple of benchmarks that shows the energy consumption of GAP8 versus a Cortex M7 ARM architecture. So GAP8, as we already said, has 8 cores, and while Cortex M7 has a dual issue 32-bit ARM core, which is also floating point. So we see that we have MobileNet that we present here is MobileNet V1 reduced, which takes in input an image which is 160 by 160 with a channel expansion factor of 0.25. And so the comparison is on energy. So we put a GAP8 at the same frame rate as the Cortex M7. So here we can see that we are there are two different silicon technologies. We use 55 nanometers, which is one generation older than the 40 nanometers that are used for the STM32. We see that the frequency to achieve the same frame rate on the ARM is 400 megahertz, while on GAP8 is 150, and we see the two different the size of the two different L2 caches. And we see that on CFAR10, the consumption in milliwatt on the STM32 is 60 milliwatt, while 3.7 on GAP8. So we see that there is a 16% of gain in energy consumption. And for MobileNet V1, we see that we have 108 milliwatt consumed for one inference on the STM32, while 7.2 on GAP8. So using GAP8, we can achieve 15 per less energy consumption. So let me introduce one of these reference design that I just presented. So it's an infrared people detector for occupancy management. So for this project, we use an 80 by 80 infrared imager by LinRed. The results that we saw for an image processing, so we need some pre-processing plus a neural network to detect the people. It's done in 62 milliseconds, consuming 4.4 milliwatt. And we have on an internally collected training set 99% accuracy. So we can see that on this reference design, using just one battery of 2.4 ampere hour, if we collect and we analyze 20 images per hour, the battery life can the battery life it's around 5 years. So we can see that while if we go to, for example, 12 analysis per hour, so what we do is we turn on the board, we collect one image, we analyze it, and we send through the network. The battery can last to up to 8 years. I mean, it is not included in this analysis, the wireless transmission. This is only the wall board collecting image and analyze it. To finish this presentation, just let me introduce our new product, which is GAP9. We learned from what we did for GAP8, and we tuned the GAP8 architecture with all the experience that we had from GAP8. We gonna change the process, the making process from 55 TSMC to 22 nanometers FDSOI, and this product will be available on boards to be bought on our website at the beginning of quarter two in 2021. Thanks. Thanks for listening. And if you have any question, you can drop me an email.